right, so let me start. Good morning. So just to briefly emphasize one of the most beautiful formulas. So we derived yesterday, sort of, not really, that the power irradiated by a system by the gravitational waves is, well, the leading order is given by the quadrupole formula, and then of course you have higher poles as well. But you know, higher pole you go, typically the signal is weaker. So this is really the leading order, and it's given by G over C5, and then simply 3 derivatives of the traceless quadrupole tensor. Okay, and so this formula, of course, celebrated great success in 1974 when House and Taylor observed, you know, this binary pulsar system. So you have this thing here, and this goes around, and so they could, because it was a pulsar, they could precisely measure the period with which, you know, this thing is rotating, and it was really, really short one. It was like 8 hours. So this is really like nothing. So they were like moving like crazy, these things, right? Because 8 hours, they have to move this whole huge distances in 8 hours. But nevertheless, they could actually observe how this period is. Okay, so the frequency is increasing, so the period is decreasing with time. And so they estimated that the system has to be losing energy, and they calculated how much energy the system is losing. And then they compared to how much energy the system would be losing if it emits gravitational waves. And so that was a precise match of the two, and this was awarded a Nobel Prize here. So by the way, I just want you to compare this quadrupole formula for gravity to the dipole formula for electromagnetism. So you see that immediately is this c cube instead of c to the 5. So that means this is actually more, you know, this will be more dominant. And so that's why, you know, people see a lot of lots of electromagnetic waves, but to measure gravitational waves is quite complicated. All right, are there any questions to gravitational waves? So I think, you know, you had Louis' talk yesterday, and, you know, everybody should jump into this, right? Because it's guaranteed that there will be lots of discoveries in gravitational waves, whereas that's not, for example, guaranteed in particle physics at this point. All right, so let me start a new section. Part B will be Schwarzschild solution. So the aim of the course here is, of course, to teach you how to spell properly some German names, and this is one of them. So Schwarzschild solution. So far, we just discussed perturbative solutions, right? So to describe the gravitational waves, it was enough to solve the Einstein equations at the linearized level. So we just perturbed the metric and wrote it as a flat metric plus more perturbation. And then that was enough to actually study the solutions, the gravitational waves. So now Einstein actually never believed that the exact solutions could be found of his equations. And so then he was really, really surprised that 1 month after he published his equations, actually Schwarzschild came with an exact solution. So the metric, which is due to Schwarzschild in 1916. So poor guy, he published the equations, and then 1 year later, he died in the First World War. Not in battle. I think he died of illness, but anyway. So you know, he could have done much more. So anyway, so the solution reads, so the metric now, which is an exact solution of equations, simply can be written as f minus f dt squared plus dr squared over f plus r squared d omega squared, where this function f is given by 1 minus 2m over r. I'm setting c's and g's equal to 1. And then this is simply a metric on a sphere. So d omega square is sine square theta d phi square plus d theta square. Okay, so that's the metric. The statement is that this is a solution, an exact solution of vacuum Einstein equations. So exact solution of vacuum Einstein equation r mu nu equals to 0. The solution obviously contains one parameter. That's this parameter m. And that is, if you want, an integration constant of your Einstein equations. M is the only parameter, and it's an integration constant. All right, so this was a huge surprise for Einstein that really an exact solution can be found, and he was really excited because he himself couldn't find any exact solutions. And in fact, to calculate the perihelion shift and whatever, he just used perturbative solution. Or to predict gravitational waves, he just used perturbative solutions. He never expected that you can actually find some exact solutions, and it was up to a different person to actually find it. And I would say this is probably the most important solution of general relativity at all. There is another one which describes our universe, FRW spacetime. And then there is a rotating version for this called Kerr solution. But these are basically the three most important solutions of Einstein equations. Are there any questions? All right, so now why is this really important? It's because of a theorem which is called Birkhoff's theorem. Birkhoff's theorem, and that says that the Schwarzschild metric, okay, so Schwarzschild metric is the most general spherically symmetric so this is important. So we are seeking spherically symmetric solutions. Solution of vacuum, that's also important. Vacuum Einstein equations. Okay, so that's the theorem. And so basically there's nothing else. If you're looking for solutions which are a vacuum and that are spherically symmetric, then this is the only answer you can write down. So now we will see that, of course, this solution does not describe, just a second, it does not describe gravitational waves. We shall see that in a minute. So in particular, it tells you that there are no spherically symmetric gravitational waves. Of course, we already know that, because we know that that monopole, which this solution actually describes, cannot radiate, and so there cannot be any gravitational waves. Yes?
Did Einstein have any suspicion that black holes existed before he saw this solution?
Sorry, before he found this solution?
Or before he read Schwarzschild's?
I don't think so. Even once this solution was known, people were very skeptical about it, and I will explain in a minute why. And so basically, the solution was there, but nobody knew what it is good for, apart from what I'll mention that in a minute. All right. So notice that sometimes people write down this Birkhoff theorem wrongly, and then they say it's the most general spherically symmetric and static solution of vacuum Einstein equations. So they are adding extra assumption that the solution has to be static, but actually that is not true. The staticity immediately follows from the vacuum equations. So if you impose spherical symmetry and you impose vacuum Einstein equations, then this already implies that the solution has to be static, and the solution obviously is static. It doesn't depend on the time coordinate t. Okay, so that's just a thing. So now how would you prove this? I'll just outline the proof. So typically people spend the whole lecture with the proof, and I'm gonna spend like 5 minutes. Okay, so what you have to do is that you have to construct, first of all, the spherically symmetric ansatz for the metric. Okay, so spherical symmetry well, what it tells you is that if I fix the radial coordinate and the time and whatever, then I have to have a sphere. Okay, so I have to have in my so ds square equals 2, and I have to have d omega square. So whatever I switch off here, I necessarily have to have the sphere. So that's why the metric for the sphere. So now in front of this metric, for the sphere, there's in principle something which is related to the radius of that sphere. Okay, so the radius could be time dependent, maybe, but let's say it is not, and I'll show you why it is not. But okay, so if it is not time dependent, I could just write some function of this radial coordinate r. But why not to write a function so that the sphere has the area 4 pi r square? Okay, so that's called a radial gauge. And so people put r square here, and this is called radial gauge. Sorry, it's called, how is it called? Area gauge. And it simply tells you that sphere has the area 4 pi r square. You can always do that by some, doing some diffeomorphism. Okay, so we have r squared d omega square. And then we dealt with two directions, with theta and phi. So now we have two extra directions, r and t. And so in principle, you could write things which have dt square and dr dt and dr square terms. But it's a 2 by 2 matrix, and you can always diagonalize it. Okay, so that's always you can do. So then it's not surprising that I can have just one function dt square plus another function dr square. Okay, so let's write it in this clever way. So 2 psi f dt square. So there's one function standing in front of dt square, and then another function standing in front of dr square. Okay, the statement is that this is the most general spherically symmetric metric you can write down. It's the most general. Spherically symmetric metric. And it's simply described by two functions, one function standing here, one function standing there, or if you want, by function f and by function psi. Okay, so that's the statement. So now, of course, people can write it differently, and then they say, well, okay, maybe I don't want area gauge. And so instead of area gauge, I can put a general function here, put a function g of r or something like that. But then, for example, you can kill this function psi, and then we have f and g of r or something like that. So there's very many gauges people use. I chose the area gauge so that I'm fixing this r square in front of d omega square, simply so that the sphere has the area 4 pi r square. But the statement is that whatever you do, you can only have two independent functions. All right. So at this point, both these functions are functions of r and t.
Could you explain again why you couldn't have like the psi f and a g standing in front of? Why only two?
Okay, I'm just saying it's only 2. I'm not really proving that. So if you are interested in the bloody all detailed proof, just look at Sean Carroll's book. But the statement is, I have to have a sphere, and in front of that sphere, I have to have something which is related to the radius of the sphere and related to the area of the sphere. If I put a function g here, the area won't be 4 pi r squared, but it will be 4 pi g squared. And g is some arbitrary function of r. Okay? And then what I'm left with is a 2 by 2 matrix, which I can always diagonalize. Right? So that's why I can kill the dt dr terms. So that's the statement. And so if I can diagonalize, it's only parameterized by 2 functions. All right, so at this point, both functions f and psi are functions of t and r, because I can diagonalize, but I cannot get rid of t and r. But it's a clever parametrization to write f as 1 minus 2m r and t over r, and then psi simply a function of r and t. Okay, so this is what I'm doing. I'm just saying these 2 functions can depend on r and can depend on t. Okay. Well, very good. So now this is all we could get from the spherical symmetry. At this point, the metric is time dependent. So we just imposed spherical symmetry, and that's it. Okay, so now it's time to impose the vacuum Einstein equations. So now Einstein equation. And the statement is that this parametrization is really, really clever to write it as e to 2 psi and to parameterize f as 1 minus 2m over r. And then what you get is that from the Einstein equation, you find that this dm, the function of r and t over dr, is 4 pi r squared. Try with your Mathematica if you don't believe me. T, that's my energy momentum tensor, and then tt component of that. And then I have dm over dt equals to minus 4 pi r squared minus dtr. And finally, I have d psi over dr equals to 4 pi r divided by f minus dtt plus drr. Okay, so this is what Einstein equations give you. All right. So now if I impose that I am in vacuum, of course in vacuum, you have T mu nu equal to 0 identically. It doesn't mean that there is no energy momentum of the gravitational field. It just tells you that there is no energy momentum tensor for the matter. Okay, so all the right-hand sides are gone now. And so the first 2 equations simply tell you that m does not depend on r and does not depend on t. So m equals to m, which is a constant. That's the first 2 equations. And then the second equation tells you that psi cannot be a function of r, it's only a function of t. Everybody happy so far? All right. So now we have, okay, so we found f is simply 1 minus 2m to capital M over r, where m is a constant. And then we still have this 2 psi, e to 2 psi, which psi can still depend on t. So now what you can do is that you can go and you can rename what time is. So now rename time. So I have e to 2 psi t dt square. Okay. So this is some function of t. So I can always find such a coordinate transformation. T goes to t prime, so that this simply goes to dt square. Okay, you can always do this, right? Well, very good. So now I just recovered the Schwarzschild metric over there. Okay. Everybody happy? That's the end of the proof. Okay. So you see that once I'm doing this, I've really shown that the solution is static, and that's very important. Questions, comments? So easy, right? Yeah.
Why do you pick the factor in front of the spherical part to be time dependent?
Oh, very good. So it's the first statement. I think you could make it time dependent. Now I'm just choosing the area gauge where I'm just saying it only depends on R and it's time independent. You could make the time dependent. It's a good question. I don't know. But yeah, I think it's still whatever I'm presenting here is correct. But yeah. Other questions? All right. So now several remarks on what happens with the solution. So now we know it's very, very important solution. It's the only one which is spherically symmetric and vacuum. Okay. So now, what are the problems into about the solution? So into the abyss. Okay. So we notice that if you take the limit R goes to infinity, and if you look at the solution, so as R goes to infinity, then this term 1 minus 2m over R simply goes to 1. And if it goes to 1, you have just minus dt squared plus dr squared plus r squared d omega squared. That's just the flat metric written in spherical coordinates, right? So we get, basically recover flat metric. So the Minkowski metric in spherical coordinates. In other words, what it means is that the solution is asymptotically flat. That's the term people use. So when you asymptote to infinity, you just get flat spacetime. All right. So now let's start looking at what happens when you actually have finite R and then you start decreasing R. Okay, so at finite R, of course, this is different from the flat spacetime. And the solution is fine until something strange happens when my f function is equal to 0. So when does it happen? So can I make f equal to 0? R equals to m. Okay, very good. So as we decrease the radius, as we decrease the radius, let's put it this way, strange things start happening. And in particular, we have a problem at R equal to R plus equals to 2m, for which f equal to 0. And so, of course, this is quite a big problem because now we have our metric. So now the first term is 0 times dt squared. So we are basically killing one coordinate direction. And then the second term is even worse because now we have dr squared over 0. And so that blows up. So actually, it kills the structure of the metric. And so there is an apparent singularity here. Okay. So I equal to 2m or f equal to 0, the metric is singular. However, as I will show you tomorrow, actually the singularity is not fatal. It doesn't mean that the space-time ends at r equal to r plus. It simply means that our coordinates are bad coordinates. So that's why this is called coordinate singularity. So remember, when we were describing the manifolds or whatever, we always chose point P, and then we said in the neighborhood, I have this region where I have a nice map to r to the n. Okay, so what we are just describing in r equal to r plus is basically the end of this region, right? So the end of the coordinate system which we are using. Okay, and we will see explicitly that you can do a coordinate transformation. You can find another patch here, and you can go through this r equal to r plus singularity, and you can extend the space time to go further through this r equal to r plus. Okay, so this is just a coordinate singularity, and if the solution can be trusted into such small radii, it would also correspond to the black hole horizon. All right, and so finally, there's another problem with the metric. So now I keep decreasing r even smaller than r plus. And then can you see another problem? Huh? Singularity at? Exactly. So now there's another problem at r equal to 0. At r equal to 0, of course, in this case, if r is 0, then f goes to minus infinity. And that's also not good, right? So r equal to 0 is and now one can show that this is a true singularity. True singularity, or the end of the space-time. It's not the end, it's better a breakdown of the space-time. Okay, and so the statement is that at r equal to 0, really, you lose the structure of differential manifold. Okay, so differential manifold, something which looks like r to the n locally everywhere. It's always look like this. The statement is at r equal to 0, the space-time will not look like that. It doesn't have the smooth structure. No matter which coordinates I choose, it will always be behaved. It will always be badly behaved at r equal to 0. So how to show this? So one way to show how to show that is to look at some scalars which may actually diverge at r equal to 0. And because it's a scalar, it will be true for any observer. So any observer who observes this thing will see that the scalar diverges, and so that means something is bad there. Okay, so one way to see this, is to look at some curvature scalars. Okay, so can you propose some curvature scalar which could be badly behaved at r equal to 0? Okay.
It's the contraction of Riemann with the Riemann tensor or with the Riemann tensor.
Very good. So you know the answer. So could I try something? Could I try something easier? So could I try Ricci scalar, for example? Is Ricci scalar divergent there? It's 0 because we have vacuum Einstein equations. So if r mu equals to 0, of course the Ricci scalar is also equal to 0. So r is simply equal to 0, and that doesn't help me. The next one you could think about is r mu nu square, r mu nu. However, that's also 0 because of the Einstein equation. So the next one you may think is it has its own name. It's called Kretschmann scalar, and it was already mentioned here. Kretschmann scalar. And it's simply R alpha beta gamma delta, R alpha beta gamma delta. So that's a scalar. It's observer independent. And then you find that this thing is 48 m squared over r to the 6. And so, of course, if I plug r goes to 0, this blows up. It blows to infinity. And that shows you that there is if nothing else, there is a curvature singularity. Okay? So that tells you there is a curvature singularity. So it's very important that you look at the scalars rather than the components of some tensor. Of course, I may be thinking I just look at the components of the Riemann tensor, and here I find that this component TRR actually diverges at r equal to 0. Well, that's very nice, but somebody else uses different coordinates, and then he will not see any divergence of components of the Riemann tensor. So that's why you have to consider scalars so that everybody agrees on the same prediction, and then one of the scalars is this one, and it tells you that there is a curvature singularity at r equals 0. Of course, this is a really big hit for the Einstein's theory, because the Einstein's theory starts from the assumption that space-time is a manifold. So now you put a metric on this manifold, and then you start solving some field equations, and then you find a solution. And the solution tells you actually space-time at this point is not a manifold. Okay, so this is really breakdown of general relativity. But it's at the same time it's very good, right? Because you don't need any other theory to tell you that general relativity is wrong. General relativity tells you itself that actually it's wrong. Okay, so GR predicts its own doom. Which is quite nice, right? So just the theory itself tells you, well, I'm actually inconsistent. You cannot trust me, into these curvatures, into these heights. Yeah.
Can't you cheat a little bit and choose u equal to 1 over r, and to get rid of singularity?
Well, no matter. Okay, so what you are just proposing here is to do a coordinate transformation, right? No matter what coordinate transformation you do, you still see a singularity curvature singularity at r equals 0.
Doesn't the existence of this singularity imply the existence of point masses? Because the Schwarzschild solution should be valid outside any finite radius. If you have some mass that takes up any finite amount of space, this solution will not be valid inside because it has some d mu. It will be a different solution.
That's right. So I will just discuss that in a minute. But here I have a vacuum solution all the way down to r equal to 0, right? So there's no matter here. What I'm describing at this point there's no matter whatsoever, right? So this is vacuum solution all the way down to r equal to 0, and then I just find that at r equal to 0 there is the end of the space-time. Yeah. So there is no mass basically here, right? All right. So these problems. One problem is at r equal to r plus. That problem is there, but it's not that fatal. You can still extend through r plus, and you can just choose different coordinates and go through, and it's not the end of the space-time. But then there is this true thing at r equals 0. So now, exactly what you said. So the question is, what is this solution good for? So what does the Schwarzschild metric describe? And so precisely what Matthias said is that we know the Birkhoff's theorem. And so we know that if you are in the spherical symmetry case and you are in vacuum, this has to be the solution. So namely, if I have a star which is spherically symmetric, so it's like stars and planets and whatever. And what I mean by this is, the metric outside. Metric outside of stars and planets and whatever. So typically you have a star which has some radius. My star. And that star has some radius. This radius is typically much, much bigger than R plus. So R plus. So the star has, okay, this will be R plus. Okay, so we don't really care about that R plus because it's deep inside the star. But if the star is really spherically symmetric, then outside of the star here, there is the Schwarzschild solution. Okay, we have a spherically symmetric vacuum solution. There is no matter outside of the star, and so outside we have Schwarzschild.
To do this, you actually have to give some sense to the m constant, right? First.
Yeah. So okay. So in this case, you can show that if you are looking at the field which is asymptotically far away, then in this case m is simply the Newtonian mass. Newtonian mass you would assign to this star. Newtonian mass. So you can look at the asymptotic behavior. You can compare to the Newtonian potential, and really you can give the interpretation of that integration constant m to be the Newtonian mass of an object. Okay. So then, for a Newtonian mass, I know that the star is 3 solar masses or whatever. So then I know that it has certain radius r, and then I can calculate r plus. So r plus is simply 2m in some screwed up units, and so for the sun, r plus is something like 3 kilometers. So now you have really, really tiny r plus of the size of 3 kilometers, and then you have size of a sun or 3 times bigger size of the sun or whatever. So this is really much, much bigger than r plus. So r is much, much bigger than r plus, so we don't care about that r plus. That's not important for us. It's not outside of the star, it's inside. But so I know that outside I have to have Schwarzschild by the Birkhoff's theorem. There's nothing else I can write down. Of course, inside I have T mu nu. So I have T mu nu of the star. The star is, to the first approximation, a perfect fluid, if you want. So it has some energy density, it has some pressures, and so on. So T mu nu is non-zero inside. And so, of course, inside the star, I cannot use Schwarzschild solution because I have non-trivial T mu nu. So what you would have to do if you want to describe the situation also inside, you have to actually study the interior solution. For the star, which I'm not going to do it here. But as I said, so basically to first approximation, you can treat the star as perfect fluid, and then just have the star filled with perfect fluid. And typically what happens is that you have to balance the gravitational attraction of this thing by the pressure outwards of the star. And then so in order to have star in equilibrium, these have to be precisely balanced. So the gradient of pressure balances whatever the gravitational force is pulling inside. And of course, what causes the pressure is the nuclear reactions and fusion and stuff like that. So yeah.
So Birkhoff's theorem tells us that Schwarzschild solution is the general spherically symmetric solution. But how stable is it to non-spherical perturbations? I mean, how does it change a lot when we use something a little different from the sphere?
Oh, that's okay. Schwarzschild black hole is stable with respect to anything.
Sure.
So yeah. So that's without the matter. So now with matter, I think you can still sort of do it if you have small perturbations and yeah.
I think it's in gravitation by Misner.
everything is.
Yeah, but it's stable.
Well, Schwarzschild black hole is stable for sure. I don't know if you start putting some matter inside the star. Well, it's just a perturbation of Schwarzschild. Yeah. It should be stable.
It's creating.
All right. Okay, so that's one thing you can describe by this. And is, really the metric outside of stars and planets and whatever. Any object that is spherically symmetric and outside its vacuum will be described by Schwarzschild spacetime. So that's why this is really, really important. So, for example, if you want to describe, what's happening outside of the sun in our solar system, then you just take, sun in the center, and then outside of the sun to the first approximation, I have Schwarzschild metric, and now I can study the motions of the planets and whatever in the Schwarzschild metric. So, second thing, which is really the new prediction of the theory, is the black holes. Okay, and so basically in this case, you just take the solution to be valid all the way till r equal to 0. Okay, so really you say, I have vacuum all the way down to r equal to 0, and that r equal to 0, my spacetime breaks down, but there's basically no energy momentum tensor anywhere. And so this is what we call black hole. Okay, and so interestingly, people didn't believe that black holes do exist, and they didn't believe until, I don't know, 80s or something like that, when actually people discovered. First, they discovered the neutron stars, and then they discovered these high energetic objects. And astronomers, who are a very tough crowd, they are very, very skeptical about anything the theory predicts, right? So it took like, I don't know, 30 years from 60s to, I don't know, 80s, 90s, that actually they didn't believe that there can be any black holes in our universe. But at this point, the astrophysical black holes divide into 3 categories, into the primordial black holes, and then the solar mass black holes, and then supermassive black holes. So these are presumably the black holes which were formed in the early universe, and they are teeny tiny, and so teeny tiny, but have not been observed yet. Okay. Of course, now solar mass black holes, they typically arise by a gravitational collapse of some massive stars. So if you have a massive star, it's just too heavy. There's too much mass, so that you can actually prevent the collapse, the gravitational collapse of this star. So there's no big pressure enough to actually balance this gravitational force. And so in the end, you form a solar mass black hole. And so these things can have various masses. And as Luis told you yesterday, is that people didn't, they expected like of the order of the solar mass object. But now, when we saw the gravitational waves, we saw 30 solar masses collapsing with 30 solar masses. So it's like really huge solar mass black holes. So this can be, I don't know, of the order 1 to order 100 solar masses, actually. Okay. So finally, you have these supermassive black holes, which actually have been observed by astronomers for a long time, and they didn't know what they are. And they call it quasars and blazars and whatever. And so they range from 10 to the 6 to, I would say, 10 to the 9 solar masses. And they are typically like, there's a huge supermassive black hole at the center, basically, of each galaxy. And so now, depending on what's nearby this black hole, and so then you can distinguish black holes either either active or not active. And if they are active, mean that typically accrete some matter. If they accrete some matter, they shine a lot, or they can even have jets. So now, depending on how you view these jets, whether the jet is really pointing towards you or not, you see different objects. And so these objects have different names because they were first observed and then only later explained that all these things are basically one black hole, one type of black hole, and it only depends on whether it's still active or not, whether it's still accreting some matter or not. So supermassive black holes. So now what is really interesting is that people don't know, as far as I know, how these were formed. So you have these, huge black holes, and so how were they formed? Nobody knows. And the reason is that there is something which is called Eddington accretion limit. Eddington accretion limit. So basically, the idea is that you start with something small and then you make it bigger by eating the nearby stuff, right? So I have a small black hole, and then this black hole accretes the stars and accretes everything around it, and so it gradually eats everything around it, and it's getting bigger and bigger. Okay, so now there's a limit which is called Eddington limit, how fast you can actually accrete matter, how fast you can eat stuff around you. And so now these objects actually have been observed like for very, very large redshifts, so very, very far away in the very, very early universe. And so you see really these supermassive black holes really soon after the Big Bang, right? But even if you accreted matter with this Eddington limit, then you wouldn't form them. Okay, it's just so now this is a puzzle at this point. Why they can be so big so early after the Big Bang. Okay, so that's one puzzle for research if you want. All right. So are there any questions? So I'm saying Schwarzschild metric very, very important. First to describe whatever is outside spherically symmetric objects, but also to describe new type of solutions. And these new types of solutions are called black holes. And we will discuss black holes in detail tomorrow. Questions? All right, so now let me use Schwarzschild solution to something interesting. And one thing which is like a first verification of general relativity, and Einstein waited only till the second day to actually show that this gives you the right thing. He formulated the equations, and he was so sure that the equations are right that he didn't calculate anything until the next day. And so he verified that there was this discrepancy, which is called perihelion shift problem. So perihelion shift and line bending. All right, so what happens with the perihelion shift is that you have your sun here, and then you have the Mercury orbiting around it. But so in Kepler theory or in Newtonian theory, these orbits are either ellipses or they are hyperbolas or whatever. But if you want a bound orbit, they are always closed. So you have a circle, you have an ellipse, but you come always to the same point where you started. However, if you have Einstein's theory, you modify your gravitational potential, and suddenly, the closed orbit is really a special property of this potential 1/r². If you perturb that potential, you don't have that. Okay, and so then what happens is that this thing actually doesn't come back to the same point, but rather makes this recession. So perihelion is the closest point of approach. So now we are here, later we are here, and so we are sweeping some angle delta phi. Okay, so that's the perihelion shift. And so this has been known for Mercury since, I think, 18th century. The astronomers measured that very, very precisely. And so the perihelion shift is actually quite big for Mercury. But almost all of it can be explained by perturbations from the other planets and stuff like that. Okay? Apart from 43 arcseconds per century. So this is the missing piece which people, were missing in Newtonian mechanics. So as I said, the precession is much, well, this thing is, the angle delta phi is much, much bigger, but all of it can be explained by using some frames, by using some perturbations from the other planets and stuff like that, apart from 43 arcseconds per century. And this was measured, so people knew that this is the case. So then the question is, can Einstein gravity predict this? As I said, Einstein waited till the second day, and he actually did the calculation. I will do it in a minute, and he saw, well, actually, this gives you precisely 43 arcseconds. So now he was really pleased and very happy. And it's like the first success and experimental verification of general relativity, as I say, like a couple of days after he formulated the theory. But interestingly, it didn't convince people that this is the right theory. Okay, and so there's always skeptics who think, well, actually, maybe Einstein just designed the theory so that it explains these 43 arcseconds per century. So maybe he just fiddled whatever he needs to do so that these 43 arcseconds actually come out. So it was like great success, but people didn't really appreciate it. Okay, so now what actually did convince people that GR is right is this light bending by the sun. So people got convinced by light bending around the sun. And so this is our sun, and this is our observer. Okay, and so let's assume that there's a star here. Okay, so now, so in the first instance, there's no sun. So if there is no sun, you would see the stars under this angle. So if no sun in front of, then you would just see the two stars coming at this angle here. However, now that the sun actually moves in front of you, and so the sun actually comes here, and then you know that the light actually gets bent. Okay, so now this thing actually travels like this. Okay, so that's the true path. And we predicted the light bending just based on the Einstein elevator. So actually, this goes much earlier to the general relativity than that one. So for this, Einstein needed to know what the field equations are. So he had to wait till 1915. But the light bending only comes from the Einstein elevator. So he knew this, I think, 1908 or something like that.
His first calculations of this, I think he was missing a factor of 2.
Okay, that's possible.
Do you know where that comes from, the factor of 2?
I don't know, but certainly the factor of 2 is also, as you will see in your homework, the Newtonian theory gives you, if you assume that it also bends light, it gives you the wrong factor of 2. So now actually, so you see the light coming from this, what it means is that you sort of see the star here. And similarly, you would see the star here. So as the sun passes in front of you, actually the angle which was originally between the two stars, this one, now becomes that one. And of course, there's a measurable effect. And this was precisely what was measured by Eddington. So measured by Eddington. of course, to see this, to see that the star behind the sun, you need a special event, and so sun is typically too bright to see any stars behind it. So he could do it only when the sign was in an eclipse. So the sun was eclipsed, and then I can see the stars behind. And so it was a very special occasion that he had to travel somewhere to actually see it. So anyway, so he measured this, and of course this was a genuine prediction of general relativity. This is something which was known for 2 centuries, that this is the problem. But general relativity predict, yeah, there will be light bending, and then you can calculate how much the light bending will be. And then it was measured only subsequently by Eddington. This is a new prediction, and so this really convinced people. So people convinced after this, and then Einstein became celebrity. Einstein became celebrity overnight. And you will calculate this in your homework. Okay, so you'll precisely calculate what the angle is predicted by the general relativity, and you can also calculate, if you push the limits of the Newtonian theory, what angle you would get, and you see that it's discrepancy by 2. Okay, but of course you shouldn't be pushing Newton's theory. Newton's theory simply doesn't really bend the light. It's the Einstein gravity which bends light. Are there any questions to this? All right, so these are really 2 verifications of GR in the early days of GR. And it's only the second one which really brought the fame. And people started treating Einstein as the prototype of scientist genius and so on. All right, so let us calculate the first effect. But for both effects, all I have to do is basically study either how the Mercury evolves around the sun or how the light evolves around the sun. And so into the first approximation, all I have to do is to study geodesics around the sun. So this will, the Mercury will will evolve on geodesic, and the sun will, the light will also go on geodesic. Okay. And so I'm helping you now with the homework. I'm giving you basically the answer for some questions. All right, so let's study geodesics around the sun. And of course, we know that outside of the sun is spherical, so around in the Schwarzschild spacetime. Okay, so the Schwarzschild metric is spherically symmetric, and consequently, as for any motion in the spherically symmetric potential, there will be conserved angular momentum. Right? So that means Lx, Ly, and Lz, they are all conserved. And so whenever you have conserved angular momentum, your motion is planar. Okay, so that just comes from conservation of angular momentum, relativistic or not, doesn't matter. So you have planar motion in one plane. Okay, so spherical symmetry means that the motion is planar. And so as always, we can choose theta equal to pi half, which is the equatorial plane. So this is without loss of generality. We can do this. All right, so that's the first step. So now the next step is to, okay, you could write down the geodesic equations and try to solve them. But in fact, you can take a shortcut, and that is to use the integrals of motion. So now the space-time is static. And so there should be the corresponding conserved energy. And then we use that once we choose this motion in the theta equal to pi half plane, then the only remaining component of the angular momentum is in the z direction. Okay, so there will be conserved Lz. There's conserved energy. And moreover, our velocity always obeys that u square equals to -1. So that's the third integral of motion. So we have static space-time. That means we have dt equal to k killing vector. We have axisymmetric after we fixed this thing here. So we have another killing vector m, which is d phi killing vector. And then we have also normalization of the velocity. U square equals to minus kappa, I'll write. So kappa is either 0 for null geodesics, or it's equal to 1 for time-like geodesics. This is 0 for null, or 1 for time-like geodesics. Okay. So now think about it. So we have the forward velocity. So we have the forward velocity u mu, which I just write dx mu over d lambda, some parameter, and then I have t dot r dot theta equals to 0, pi half, so theta dot is equal to 0, and then phi dot. So that's my forward velocity, which describes the geodesic. So we effectively killed one of the components, so we have only 3 degrees of freedom left. We want to find how t, r, and phi actually behave. But we have 3 integrals of motion. We have energy, we have angular momentum, and then we have normalization of the velocity. So we have 3 degrees of freedom, and we have 3 integrals of motion. Motion, which will be energy, L, and kappa. And so the motion will be what? If I provided that these integrals of motion commute to be integrable. So the motion is completely integrable. Which means, by definition, we can integrate it. All right, so let's have a look at that. So I just remind you that, you know, if you have killing vector, the static killing vector, or whatever, then you can form out of it the conserved quantity for the geodesic motion. You simply take that vector k and multiply it by the velocity, and this is conserved along the geodesic. You had the tutorial and you did that. Okay, so we have the energy is given. So now by convention there's a minus sign for the energy. So it will be vector k mu u mu. Okay, so this is my vector k, which is the static killing vector, and then I have the corresponding velocity, and this will be conserved, and I'm just taking minus. Okay, so now what k mu? So u mu is this thing here, and then k mu, if I write index 1, index up, it will be just 1, 0, 0, 0. But now I have to write the index down, so I have to lower it with the metric. And I'm lowering this GTT component of the metric, and so that's minus f. Okay, so this is equal to minus GTT t dot, and this is equal to f t dot, using the form of the Schwarzschild metric. I just remind you, so the Schwarzschild metric like this. All right, so this is my GTT component is f. Now I have another concept quantity, which is the angular momentum, which will be given by the other Killing vector, u mu, now with convention plus mu u mu, and that's simply g phi phi, g phi 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 dot, and that's r square phi dot. And then we have this minus kappa equals to u square. And u square is simply, I see the metric and I replace wherever I see d, I just replace it with a dot. So this is minus f d dot square plus r dot square over f plus r square phi dot square. So these are my three integrals of motion. And I can solve them for t phi and r. Is this clear? Is it fine? Is it boring? Probably boring. All right, so this was basically given to us for free. So now let's combine all three equations to one equation for r. Okay, so we have this equation minus kappa is minus f t dot square plus r dot square over f plus r square phi dot square. And let's just substitute for t dot and phi dot from the other equations in terms of this E and L. Okay, so then I have minus kappa equals to minus f. Okay, and then t dot is E over f. And then square. That's t dot square. And then I have plus r dot square divided by f. That's the other term, which, okay, is there. And then I have plus r square. And then phi dot. So phi dot is L over r square from the second equation. And then square. Just plugging the first two equations into the third one. All right. So now what you can do is that you can multiply everything by f. Okay. And then you can divide everything by 1/2. And then you can reshuffle the terms. And so what you find from here is that 1/2 r dot square plus something which I call v is 1/2 e square. And then if you just look at this equation, the v is simply given by 1/2 f kappa plus L square over r square. Or if I plug what f is, so f is 1 minus 2m over r. Kappa plus L square over r square. All right, and then if you expand that, this is given by kappa over 2 minus kappa m over r plus L square to r square minus ml square over r cubed. And it's called effective potential. All right, so we found that our radial equation looks like this. It's 1/2 r dot square plus some effective potential equals to 1/2 the energy square. And the effective potential looks like this. And this is the starting point to discuss all kind of geodesics in the space-time. So you will have to reach here probably when you study your light bending in the homework. And then you just simply say, well, I just want to study null geodesics in the homework, so I'll plug kappa equal to 0. And so this simplifies the first two terms are gone. And then you just start studying your light bending. So now I want to discuss the perihelion shift. So I'll concentrate on the time-like geodesics. So I will just take kappa equal to 1. Okay. So we concentrate, we study perihelion shift. And so set kappa equal to 1 because we want to study the Mercury, but Mercury has to move on time-like geodesics. All right, so our effective potential is just V is equal to 1/2 minus m over r, and then plus L square over 2r square minus ml square r cubed. By the way, if you compare this to the Newtonian potential, if you just did the same analysis, but now with the Newtonian physics, not with the Schwarzschild solution, but it's just a standard Kepler problem. Of course, you are free to shift the energy as always, and so I can arrange that the Newtonian potential will also have this 1/2. Typically, when people study this in Newtonian potential, they choose this 1/2 to be equal to 0 actually. But anyway, so you can shift the energy wherever you want. So I'll put this 1/2, and then you would find that these three terms actually are Newton. Okay, so if you did study the same problem using the Newtonian mechanics, you would find the first three terms, but this is the GR correction. Only the last term is actually what is new in general relativity. Okay, but as you will see, this term is quite interesting, and it changes completely everything as you approach small radii. Okay, so one thing you can look at is that you may be asking, well, we will see that when we study this potential, it has typically some maximum and some minimum, or it doesn't have any maximum and minimum. And of course, the limiting case when one case happens when you have maxima and minima and then you don't is if you have an inflection point in your potential. So to study an inflection point, of course, inflection point of the potential happens when v prime equals to 0 and when v double prime equals to 0 with respect to the radius. And you can show that this happens when L square equals to 12 m square and then r equals to 6m. So something interesting will happen when r equals to 6m and when L square equals to this value here. So I have two equations. I can just use this, differentiate twice or once, and then solve it for L and for R. All right, so now what happens? And any questions so far? No. I think, compared to the gravitational waves, this is super simple, probably. All right, so then we can plot this effective potential. And then you will have two cases. Either L square is bigger than 12 m square or it's smaller. Okay, so now if you plot for bigger, So case 1 is when L square is bigger than 12m square. And that actually means that you will have maximum and minimum. So this is your potential V, and then this is my R. And what you will find is that there is a minimum, then there is a maximum, and then it goes like this. Okay, the value here is 2m. The minimum is bigger than 6m, so there'll be 6m here. So 6m is precisely where the inflection point is. So once we have maximum minimum, the radius will be either, well, for minimum it will be bigger than 6m, and for maximum it will be smaller than 6m. Okay. So if you plot it, what the Newton would give you, so the Newton wouldn't have this last term, and so it wouldn't turn to these negative values like crazy for small r, but instead it would go like this. So this would be the Newton, and this is the GR prediction. So now, of course, here at the very bottom, I can have stable circular orbit. And the possible motions depend on what your energy are, what your energy is. So I can have only motion, r dot can be non-trivial, if energy is bigger, if 1/2 e square is bigger than v. Okay, so if I have 1/2 e square, let's say this value, and I'm bigger than v, I can have motion from this radius to that radius. In Newtonian theory, that would correspond to an ellipse. But in our case, we have this shift of the perihelion. And here I have a circular orbit, but of course here, my 1/2 e square is smaller than v, and so I cannot have motion here. Okay. So now you see a qualitative big difference. So Newton, so if you have, angular momentum for Newton, whatever the energy I have, and I shoot it here, I will never fall all the way to the r equal to 0, right? I will always turn back and then go back, and this would correspond to my hyperbola. But I never, in Newtonian theory, I can never reach r equal to 0. However, in Einstein theory, of course, I can do it if I have sufficiently high energy. So here, I would just hit this wall here, but if I am above, I would actually go all the way to r equal to 0 in Einstein theory. All right, so that's one possibility. The second possibility is more boring, and that's when r square equals to is smaller than 12m square, and then simply in this case, it would just go down. There is no maxima or minima, and this thing looks like this. And again, this would be the Newton thing, but here I don't have any bound orbits. So no bound orbits. No bound orbits in GR. So simply, if your angular momentum is too small, you just, you are sucked by your potential, and you go all the way up to r equals 0. All right. So now we want to describe. So now we understand everything. So this is certainly what this does not apply to Mercury, right? So Mercury is basically it's certainly on a stable orbit, but it's not the circular orbit, but it's almost the circular orbit. It's somewhere here, right? It's changing the radius a little bit, but it's actually not that much. So I'm actually close by to stable circular orbit for the Mercury, and it's this case. So in fact, L square will be much, much bigger than 12m squared. Okay, so case 1 applies for Mercury. All right, and so now you can actually go and study what is the corresponding trajectory, and what happens, how to solve all these equations here. So typically when you want to solve for trajectories and you are just interested in the shape of the trajectory rather than how the trajectory evolves in time, what you do is that, well, here you have like dr over dt, and then this equation gives you d phi over dt. Okay, now you divide the two and you have dr over d phi. So how my radius depends on the angle phi. So now this is a nasty equation. It's a first order equation, but it's a nasty one. So then what you do in Newtonian theory is that you differentiate this equation and you get so-called Binet's formula. So you have now second order differential equation, which basically looks like a harmonic oscillator plus some perturbations. Okay, so then you solve it perturbatively, and so you can find the trajectory here. Okay, so so in Newtonian theory you can solve it exactly. In general relativity, if you did the same thing, you would have to solve it perturbatively. It's a nice exercise. It takes several pages, and it doesn't really answer the question which we have. So how much, how fast the perihelion actually is shifting during the time. So that's why actually I'll use the shortcut done by Wald, and it's basically three lines. All I have to write. So okay, so if we have the Mercury, and we know that the trajectory is almost circular. So I'll write the circular trajectory as RC. And actually, we are very, very far away from this gravitational radius of Schwarzschild. So this is much, much bigger than m. Okay, so the Schwarzschild radius for the Sun is 3 kilometers. Mercury is of course much, much farther away than 3 kilometers from the Sun. All right, so we have that. So now the next step which we have to do is that we have to solve at which radius we really have this circular trajectory. So we have to solve what RC is. Okay, solve for RC. Okay, how do we find RC? We have the potential. What do we need to do? You have to find the minimum for the potential. So we take V prime equals to 0, V prime equals to 0, and take the larger root, because the smaller root will give us this circular trajectory, which is unstable. So we take the larger root. Okay, V prime equals to 0, and take larger root. All right, so one should never differentiate in public, but let's see. So we have V. So V prime is, okay, so 1/2 at 0. And then we have plus m over r square. M over r square. And then we have minus 2l square over r cubed. Minus L square over r cubed. And then we have plus 3ml square over r to the 4. Okay, so this has to be equal to 0. And now we have to solve it for something. Okay, a stupid idea would be to solve it for RC. Why is it stupid? Because this is a quadratic equation. Well, it's an ugly equation, right? It's a cubic equation. Okay, so let's solve it for something else. Let's solve it for, let's say, L square. L square is linear here. So why not? Okay, so we have that m over r square is L square over r4. And now this is disaster, minus 3m. Is that it? 3m L square over r4. Yeah, that could be that. L square r cubed, 3m L square. Yeah, is that it? Maybe. Okay, so from here, of course, this is at r circular now. So from here, we see that L square equals to RC square M divided by RC minus 3M. Okay, we just solve what is the corresponding angular momentum in terms of the circular RC. So far, so good. All right, so now we know where the circular orbit is, or at least what is the corresponding angular momentum. So now what we are really doing is that we have to calculate what is the frequency around which, with which we are oscillating around the minimum. So as we are here, we'll be oscillating in this way around the minimum. And the corresponding frequency is simply given by two derivatives of my potential, right? So the first derivative of the potential around the minimum is 0. So basically what we are doing is that we are linearizing the potential around the minimum. And then the frequency, so we know that omega r square, which is the frequency with which we oscillate in the radial direction around, is simply given by two derivatives of the potential RC. Okay, so now I'm not going to differentiate this again, but you could of course do it. So differentiate this v prime once more. And then the result will depend on L square, but I can plug for L square from here. Okay, so I'll just eliminate L square. And so what you find is that this is equal to M RC minus 6M divided by RC minus 3M and then RC square. Okay, so this is the radial frequency. Radial frequency. But then you also may be interested in the phi frequency. What is the frequency I'm going around in phi direction? So then we have angular frequency omega phi square. Well, that's nothing else than phi dot square. But from that equation, phi dot square is L square over R to the 4. Okay, so this is L square over RC to the 4 from this equation here. Again, I plug in 4L square, and this is M over RC square, RC minus 3M. So whenever you see M, it's small, right? So M is small with respect to any other radii which we have here. So if you want to recover the Newtonian gravity, you just plug everywhere M equal to, well, not everywhere, but whenever you have whatever you are comparing something big and small, just plug that equal to 0. So then the radial frequency would be just M RC over RC cubed. And so this I neglect and that I neglect. And then this one would be M over RC square and then RC. So it's M over RC cubed. That's interesting. Anyway, so that's the angular frequency. Okay. So now if these two frequencies are the same, I'm probably missing something. RC. Should it be RC cubed here? RC cubed, maybe. Oh, it doesn't matter. All right. So now if these two frequencies.
How did you get omega phi?
It's just this thing here. So omega phi is just phi dot, right? So phi dot is L over R square. Okay. So now I have the frequency in the phi direction, and I have a frequency in the r direction. If these frequencies are the same, then actually the orbit is closed, right? So I'm oscillating in this direction, and I come after some time to this point, and I'm oscillating around that direction. And if I, at the same time, I come to the same point, then the orbit is closed. Okay, so if the frequencies are the same, frequencies the same, then we have closed orbits. So now the point is that, of course, they are not the same. They look the same, but not really. And there are these general relativistic corrections. And so what you can define is that you can define the omega precession is the omega of the angular frequency minus omega of the radial frequency. And if you plug it here, you take the square root, take m to be small, you find that this is something like 3m to 3/2 divided by RC to 5/2. And this is precisely how fast the angle is precessing. So this is the precession frequency. Okay, and so this is the frequency. And if you are interested in how much angle is swiped, you just multiply by 100 years. That's my century, and you will find 43 arc seconds. Okay, so this is all you have to do is to calculate these three lines here, and this is the frequency with which the angle phi is actually moving, the perihelion shift. So if you want, I can give you an isoformula per orbit. So per orbit, I just have to multiply this. So delta phi is simply t times omega p. So this is the orbital time, period of orbit. And now you can use Kepler's law, where you know that t squared equals to 4 pi RC cube over m. That's what third Kepler law gives you. Like t squared is proportional to RC cube, r pi square. And then if you plug it in, you find 6 pi m square divided by L square, which is the formula Carol derives in, I don't know, 5 pages. You see that we started here and we end up here. So it's like half the page calculation, several line calculation. All right. But of course, if I'm interested in century, I don't plug one orbit, but I plug 100 years here, and then you'll find 43 arc seconds. Okay, are there any questions? Yes?
Does it mean to have RC like less than 3m? Because in this case, L squared will be negative.
Say it again.
Have RC less than 3m.
Oh, right. So we can't have that. So remember, I didn't stress that enough, but there's this thing here. So r equal to 6m is really important, and so that's the position of the inflection point, right? So that's the point where the potential sort of looks like this, right? So now if I want to start making it with the maximum and with the minimum, okay, the minimum will be always bigger than r equal to 6m. So this thing has always r bigger than 6m, and the maximum will always have r smaller than 6m. So now we want to describe the circular orbit, and so that will always be located at r much bigger than 6m. Thank you for that question. I should have stressed that. So this is really telling you all the stable circular orbits have to be bigger than 6m. Other questions like this? That's an excellent question. All right. So now this was the first success of GR, the prediction of this thing, and tomorrow we will discuss finally the black holes. Okay.